And continuing with tonight's lectures, now we have our second speaker, Dr. Bradfor Robertson. He is a research engineer in the Defense and Space Division of the Aerospace System Design Laboratory, also called ASDL, at the Georgia Institute of Technology. He holds a master's degree and a Ph.D. in aerospace engineering, both from the Georgia Institute of Technology. He has worked on projects involving military operation analysis, airline schedule optimization, aerospace manufacturing, entry, descent, and landing system, space vehicle design, and missile design. His current research areas are high-speed aeromechanics and flight dynamics, as well as the sizing and synthesis of space systems, space architectures, and high-speed atmospheric vehicles. He's also the technical advisor to the ASDL's missile design competition teams. I leave you with Dr. Bradfor Robertson and his talk, Lunar Exploration Architectures. Welcome, Bradfor. This virtual floor is yours.
All right, thank you very much. I'd like to thank everyone in attendance for your attention, and thank you for having me. So let me share my screen. Here we go. Is that coming through? All right. So yeah, so this evening I wanted to talk about lunar exploration architecture. So I kind of wanted to start this out with some of the very basics of space mission engineering, and then kind of go through like a lot of the decisions and the specific aspects of what was going on with the decisions going into both the Apollo, Constellation, and today's Artemis program. So to start out with, right, at the very basics, right, a space mission is really just the objectives, orbits, maneuvers, events of a space vehicle. And so we say objectives, so those are like, your requirements. What are we trying to do? For satellite systems, those are going to be things like performing observations, sending and receiving signals. For more crewed systems, that's going to be life support, transportation, etc. Right? The orbits are going to be the set of orbits to be traversed during a space mission, for which there's a large trade space when you start to get to lunar exploration and especially Mars exploration. And then finally, all of the maneuvers and events that, how do you traverse those specific orbits? So in my line of work, generally, I tend to focus a lot more on how big things are, what are the physics-based sizings, and for that, I really tend to think of space missions as a series of orbits. How do I go from one orbit to another? What are the maneuvers that need to happen? What are the configurations of spacecraft as they come together, do on-orbit refueling, undock, perform lunar landings, etc.? And so let's get into a little bit of what is an orbit. So for those of you not familiar with that, so orbits are just very simple orbital or elliptical paths, right? Technically, we're all right now in orbit. We're just, constantly intersecting the Earth where it's providing us a normal force. So if you fire any sort of projectile, that's going to follow an elliptical trajectory that's going to intersect back within the Earth. At some point, you go fast enough that you actually go ahead and you start circling the Earth again. And then finally, you might get fast enough that you actually have an escape trajectory. And so all of this is just a fundamental specific energy. And so you can see this in both the kinetic energy and the potential energy of a system. And so here's basically an example here on the actual specific orbital energies in meters squared per second squared. So just from the news lately, I'm sure you'll have seen Blue Origin and Virgin Orbit actually do some suborbital flights. Those actually are very, very tiny amounts of energy required, especially when compared to with something like what's ISS or a Falcon flight. And then up here, you can see this is where we get to geosynchronous orbit. And then further on, you can start to get to, say, the Lagrangian points and to lunar translunar injection. And so that's just kind of giving an example of, what are all of the relevant energies in play here. Now, unfortunately, that kind of brings us to the tyranny of the rocket equation. So all space missions are acceleration missions. So when I lecture to students, right, I generally make a big distinction here. So any other transportation mission say it be an aircraft or even just just driving in your car, right? Those are generally cruise missions. I'm generally traveling at nearly a constant speed for some amount of time to get from point A to point B. Whereas with space missions, we're generally trying to change the energy state that the spacecraft is in. And so you can see here, this is the basic example of like a very basic orbit transfer. You would have one burn to raise your orbit, and you would have a second burn to circularize into a higher orbit. And so generally what we refer to as each of these burns is the change in velocity at each section, otherwise known as delta V. And so space travel is governed by this innocuous looking equation here that is known as the rocket equation. And so fundamentally what that's modeling is the conversion of propellant to a change in energy state by a propulsion system. And so it's an exponential effect. So for every additional kilogram of propellant that I carry with me, I have to carry additional kilograms of propellant to propel that propellant that I just carried. And then that's going to compound until eventually I actually close my system where the amount of delta V that I need is equal to the amount of propellant I have on board. Now, this is very much a diminishing returns capability, which is why you see spacecraft stage. Right? I mean, that's the only transportation system where up until Falcon 9, you generally throw away your stages as they go up to orbit. And so that's generally why that occurs, is that we need to throw away as much mass as we can in order to just be able to accelerate more efficiently. And so, and I'm going to go back to this chart throughout the course of this, because this does a good job in illustrating the relevant delta V's and transit times in the cislunar system. So, for example, so the amount of delta V needed to reach a low Earth orbit is about 9.4 kilometers per second. So that's not on this chart. That's just, so if you have a launch vehicle that has 9.4 kilometers per second of delta V in it to get to low Earth orbit. Now, if I wanted to go from low Earth orbit to low lunar orbit, so that would be traversing here up into low lunar orbit, that's about 4.1 kilometers per second. The delta V from going from low lunar orbit to the moon's surface or back into low lunar orbit, so that's about 4.1 kilometers per second. So that's just going to and from the surface. And then, of course, I need another 955 meters per second to go from low lunar orbit to the Earth. So if it was a pure Apollo-like lunar mission, you're looking at a total of 18.5 kilometers per second between launch to low Earth orbit and then 9.1 kilometers per second of in-space delta V. So that's generally, I just wanted to give you all an idea of what are the orders of magnitude that we're looking at in terms of the amount of energy change that's needed within the Earth-Moon system. And so that brings me to how do we achieve this delta V? So spacecraft propulsion. So in-space systems generally have two propulsion systems, especially for these large like crewed systems, right? So there's usually a main propulsion system. So this is the Apollo, the Apollo command module and service module. So main propulsion system, that's going to have your high thrust rocket engine to do your large burns. You don't want to do that with small burns unless it's an electrical system, just because you're going to have a lot of delta V losses, and that's going to lead to even more propellant needed. So this is almost always a bipropellant engine. And then you also have these reaction control systems. So these are very small. They're almost always made up of storable propellants. They could be bipropellant or monopropellant thrusters, almost always pressure fed because you want to have very quick response from there. You usually have those in clusters of 4 so that you can get moment control over there. And while that does provide some attitude control, one of the primary things that this does, especially in satellites, is that it helps de-spin a lot of your internal systems, such as control moment gyroscopes or reaction control wheels. So most spacecraft generally have these two propulsion systems. Some have more. we're now starting to get into, it's very interesting right now in the world of in-space vehicle design, because we're starting to explore a lot of hybrid systems where they have different propulsion systems on board. A lot of what we're looking at for Mars systems are things like nuclear thermal, or nuclear electric and chemical, or solar electric and chemical. So there's a lot of interesting things that are happening, but that's generally the breakdown that happens. And so just wanted to go into a little bit more about propellant choices. So I'm going to primarily stick to chemical here and not go into anything very exotic, because we've only flown either chemical propellants, or we have one or two missions, exploration missions that use electric propulsion. So monopropellant, such as just hydrazine, right? That's a mixture of oxidizer and combustibles in a single compound. So it's very simple. It's usually pressure fed. I just have simple tankage, but unfortunately, it's very low performance. And so that's kind of the trade-off there. Most everything that you use for a main propulsion to do the majority of that delta V is going to be a bipropellant engine. So for a lot of what was used in the Apollo program, you end up having some storable hypergolic propellants, so such as hydrazine and nitrogen tetroxide. Now, those are very toxic, lower performance, but very useful for in-space propulsion. And those are very useful because those combust on contact. So I can just put in a pressure-fed engine, open some valves, and I have thrust. So the other three are generally, so far, generally tend to have been used a lot more for launch vehicles, but we're starting to explore their use in in-space vehicles. So RP1, or kerosene and liquid oxygen. So that's primarily used for first stage launch vehicle propulsion, because in your first stage of a launch vehicle, you need a lot more thrust to overcome your gravity losses to get you going. So this has been used, is still in use today. That was the first stage of the Saturn V. That's the first stage of the Atlas V. That's all of the stages of the Falcon series. And so one kind of drawback on this is that liquid oxygen is cryogenic, so that has a 90-degree Kelvin boiling point. And so another propellant combination that we're starting to explore a lot lately is liquid methane and liquid oxygen. So it has some advantages in that it has higher performance than just kerosene, but the liquid methane is cryogenic with a 112-degree Kelvin boiling point and less dense. So I'm going to have a lot more mass in my tankage structure to accommodate the same amount of energy that kerosene would have. However, this is a lot more useful for reusable launch vehicles, which is generally why you see Starship and Super Heavy start to use this. So one issue that RP1 has is that there's coking and soot issues. So when you turn the RP1 system off, they're going to have a lot of propellant soot built up in there that you have to go rehabilitate and clean out. Whereas if you have liquid methane, that's just going to boil off and you're not going to have as much stuff to clean. Now, the highest performing chemical propellant are liquid hydrogen, liquid oxygen. Now, liquid hydrogen is very cryogenic at 20-degree Kelvin boiling point. So that's very difficult to maintain. And there's a lot of investment from NASA into how do we start to maintain that for in-space usage. Also, the density of hydrogen is very much an issue. So while hydrogen is very energetic and I don't need as much mass of hydrogen compared to other systems to get the same amount of performance, it's not dense at all. So if you see a space shuttle or now a SLS that uses hydrogen systems, the vast majority of the size of that launch vehicle is the hydrogen. That's 70 kilograms per cubic meter. And that's generally an issue because now I have to have much larger tankages. If I want to keep that cool in space, I have to have even more insulation, or if I have an active cryo cooler system, that's even more area that I need to cover. And so my final propulsion chart is kind of, here's the engine cycles of how these things are actually used. So as I said before, you generally have pressure-fed systems where, I just open a valve and then I, put those into a combustion chamber and I accelerate flow out the back. Then after that, we start to go to turbo machinery based cycles. So the most basic one is a gas generator cycle where I utilize my fuel and oxidizer to burn a gas generator, to spin a turbo pump, to feed fuel into my main combustion chamber, and anything within my gas turbine that tends to be dumped offside or offboard, overboard as exhaust. So for example, the F1 engine and the Merlin engine SpaceX are gas generator engines. The expander cycle, that's what the RL-10 uses. That's the most efficient liquid hydrogen and oxygen engine that is made. And so that utilizes the heat coming off of the rocket engine that it regeneratively cools to expand the hydrogen and run a gas turbine engine. So that's pretty efficient. And then, of course, the most efficient is the staged combustion cycle, where we essentially have a pre-burner where the outcome of the output of the pre-burner goes and runs a gas turbine similar to a gas generator, except that instead of dumping the exhaust overboard, that goes back into the combustion chamber and contributes to the overall thrust of the vehicle. So that's what the space shuttle main engine uses. The Russians were very good at making staged combustion engines. We fly those with the RD-180 on the Atlas V launch vehicle. And now SpaceX is utilizing a variant of this engine cycle for their Raptor engines, which I think probably SpaceX's Raptor is probably the best engine that's currently made today. And so I kind of just wanted to wrap up like the very high level basics of what's going on there. And so that goes into kind of what are my key decisions. So what's my orbit design? So what orbits are needed to execute the space mission? And that provides the delta V budget. And that's how do I account for all the delta V needed to execute this between all of the different events that I need to work with. Then I work with how do I split that delta V budget into stages and which elements perform which burns and how are those constrained to fit on a launch vehicle? And then what is the propulsion system for each stage? So that's where you would look at what are my engine cycles, what are my propellants, and then you generally have trades between cryogenic systems and storable systems. So cryogenic systems are higher efficiency, but one thing that I do want to talk here, especially for in-space systems such as hydrogen, oxygen, and methane, is that in space that will boil off, and I will lose. And then the longer I idle in space, I will lose my propellant. So that needs to be accounted for. Versus the storable systems that are, like I said, more toxic, less efficient, but they have high density and don't boil off. So those are the general trades that we have to make. So how does this work with Apollo? So as you'll know, right, Apollo started in the 1960s with President Kennedy's challenge to land a man on the moon and return him safely to Earth in a decade. So that was a very politically significant program, right? So at the time, the United States was appeared to be behind in space and missile technology between Sputnik, Yuri Gagarin, the Cuban Missile Crisis, the Missile Gap, etc. And so that was very much a figurative competition. And so the interesting part there, right, was in terms of like your programmatic constraints, you almost didn't have a budget constraint. They were spending 4.41% of the US federal budget at its peak. So that's the equivalent of $47 billion a year in 2020 dollars. So while there was no real like budgetary constraint, they were constrained in time as well as technology because they had to invent all of this from scratch. And all of that ended up with the 1969 crewed landing, which was very hard fought success. And so starting with the orbit design. And so this was one of the key decisions that actually enabled the 1969 landing to occur. So at first, the idea was that we have a direct launch. So that was advocated by NASA headquarters, where you have one launch from Earth that goes just straight to the moon, lands, comes back, and everything on one rocket. And that required, at the time, what was called the Nova rocket, which would have been even bigger than the Saturn V. Earth orbit rendezvous at the time was advocated by Wernher von Braun at NASA Marshall in Huntsville. And so that required 2 launches of Saturn and would do a similar mission around the moon, but both would dock in Earth to assemble into a much larger vehicle. Now, what actually ended up happening, and this is one of the interesting stories of Apollo was that the lunar orbit rendezvous was the lowest mass. I could have one launch of a Saturn V, and then I would split my stages between going to the lunar surface and having the return stage stay in orbit. So that's really what saved a lot of this. And it was considered difficult at the time because when this was proposed, we had not yet conducted on-orbit rendezvous, much less a docking. It was considered very difficult to do that in lunar orbit. And so in order to execute this lunar orbit rendezvous, they had three elements to the system. So they had the Apollo Command Service Module, the Lunar Module, and the Saturn V launch vehicle. And so going back to this chart, so the Saturn V launch vehicle performed the 9.4 kilometers per second to get into low Earth orbit, and then it performed the translunar injection. The service module performed this low lunar orbit injection. Then the lunar module had a descent element, which performed this 21 kilometers per, or 2.1 kilometers per second descent to the moon, an ascent module that went back into low lunar orbit, and then the service module provided this final 955 meters per second to get back into Earth. So that's how all of that worked. So for Apollo, the service module, so that's split up here. So this is service module versus the command module. So basically everything in the vehicle was in the service module. That was main propulsion, electrical power, eclipse, communications. So that used storable fuels of Aerozine 50 and nitrogen tetroxide, and ISP of 314 seconds. The command module, well, that carried the crew, had crew supplies in there, such as food, anything they needed to access. Was very limited in the amount of actual, transportation that it had. It had a small reaction control system, and that was mostly to orient itself during Earth reentry. Finally, there was a launch escape system. I'm not going to talk much about this, but that was jettisoned during liftoff. And so that was actually a really cool video, if y'all can find that on YouTube, of them testing this on a rocket as it was disintegrating. So fortunately, we never had to use this with crew on board. Similarly, the lunar module, that was a two-stage setup with sim propellants, about the same ISP for those. And so the descent module performed the more Delta V heavy descent while carrying the ascent module, and then also served as the launch pad for the ascent stage. That, of course, the ascent stage was also the crew component, and it had all of the necessary eclipse systems for that. And by far, the ascent module was the most mass sensitive part of the vehicle, right? That's the part that experiences the most Delta V. So that's getting pushed around the most, that's getting launched, that's going to TLI, that's descending to the lunar surface. And then that's also going back up to low lunar orbit. And so it was very interesting how they designed that. The original concepts had like seats, larger windows, and they had to get rid of the maximum amount of mass in order to get that to work. And then wanted to talk about, say, like the Apollo Saturn masses. So this was interesting, right? I hope all of y'all can see this. So this was just under 3 million kilograms for the total stack, everything launched. So this is all from a document called Apollo by the Numbers that actually is very interesting. It has all the detailed information for each of the Apollo flights. The launch payload rated here was 49 tons. And when they say that payload, right, that's payload into translunar injection, but it's really 4,500 payloads to translunar injection because they consider this 4 tons of the launch escape system to be payload. But in actuality, right, the command module, service module, adapters, lunar modules, those are all payload to the Saturn V. And of that 45 tons that are launched in the translunar injection, most of that payload is fuel. So of those 45 tons, 28 tons are fuel, and the crew is only rated here at 488 kilograms. So just to let y'all know, like this is why it's tyranny of the rocket equation, right? Is like I need all of that fuel in order to just execute that mission. And so just wanted to finish up here at Apollo. here's the actual stages, right? So you can see here the inertial velocity over time for each of these stages to get to orbit. So you can see here the Saturn 1 stage, that was with a LOX RP1 system with 5 F1 engines that was very much optimized for high thrust takeoff and getting up to speed. The majority of the Delta V to orbit was done by the Saturn V second stage that used 5 J2 engines that had liquid oxygen and liquid hydrogen. And so that was an average ISP of 421 seconds because you were still very much in the atmosphere as you were starting to go forward. And then finally, the S4B is the third stage. That was 1 J2 engine during ascent that really only provided just 1 kilometer per second, but the majority of that it performed was the translunar injection burn. And some of those are still in space today. Our on-orbit sensors have spotted one of those in a very highly elliptical orbit around Earth, coming back every once in a while. And so that was Apollo was a very successful program, right? And that kind of just ended a natural death as we won the space race. It was very expensive. And we wanted to move on to other things that we thought were going to be more sustainable with the idea of the space shuttle. So now I want to talk about the Constellation program. So in 2003, we unfortunately lost one of our space shuttles in the Columbia accident. And so after a lot of soul searching after that, it was essentially decided that we wanted to move towards exploration. We wanted to take a higher view towards crew safety. And the biggest part was we did not want to launch the crew alongside with the cargo because we wanted to have a much more highly reliable, safe crew system, and then we could have less reliable cargo systems. And so kind of the idea behind Constellation was that we had the space shuttle that existed. If you think about the space shuttle, that was already a heavy lift launch vehicle, but most of the payload to orbit returned to Earth with the shuttle orbiter itself. And so the idea was like, could we use shuttle-derived launch vehicles to conduct space exploration beyond low Earth orbit? And so that really started out with a study called the Exploration Systems Advisory Study in 2005 that kind of gave the idea of a 1.5 launch architecture, which I'll get into. And then that eventually matured into what was called the Constellation program, which lived on between 2005 and 2010. And as I said, right, emphasis on crew safety, trying to maximize reuse of the existing technology we had from shuttle, as well as the existing industrial base, because they didn't want to have to lay off the thousands of workers from that ran the shuttle program, lay them off, and then say, oh, can you all come back in a few years and run our space program? That's not going to work. And so that had a 4-element lunar architecture with the Orion crew vehicle, pictured here, the Ares 1 crew launch vehicle, the Ares 5 cargo launch vehicle, and the Altair lunar lander. And so this was by far the biggest change to US space policy since the adoption of the space shuttle. And so this was a typical lunar reference mission with the Constellation architecture, was that it was both Earth orbit rendezvous and lunar orbit rendezvous. And so the idea here is that you would have a cargo launch vehicle that would have the Earth departure stage and the lander launch on one launch, and then you have the crew and the Orion launch on a second launch. So that's what they mean by kind of 1.5 launches, is that this is, say, half the launch vehicle that this is. It doesn't really work out that way in terms of costs, but that was the idea. These would rendezvous at Earth orbit, and then the Earth departure stage would perform a translunar injection, at which case the descent module of the lander would perform lunar orbit injection and then would perform the descent. There would be an ascent element similar to Apollo that would return the crew back to low lunar orbit, and then the Orion service module would perform the trans-Earth injection to return the crew back to Earth. And so the idea behind this was that, hey, what if I bought two launch vehicles for the price of one, was kind of the idea. And so at the time of the cancellation of the Constellation program, the Ares 1 was already well into development. So that we had the five segment solid rocket booster was underway. The J2X upper stage engine was designed and they built the test stand for it. They were in the process of creating the tankage for the Ares 1 upper stage, and the Orion program had been underway for a few years. However, the idea was that we were going to utilize this J2X engine and the 5-segment solid rocket booster to help build the Ares 5 heavy lift launch vehicle. So you would use this engine for the Earth departure stage, and you use the solid rocket booster for the first stage. And so within that architecture, there was the Orion crew module. And so that had 4 elements of very similar to Apollo, of a command module that would house between 4 and 6 crew members. So that was literally just geometrically scaled from the Apollo. It's really amazing when it's, you know, we live in 2020, or at the time it was 2006, 2007. And even with advances in technology, we would look back and say, yeah, so those designs back in the 60s were pretty much optimal for what they were trying to do. So, and that was 5 meters in diameter versus 3.9 for Apollo. So the idea was that we wanted to carry much more crew to the moon, and also possibly 6 crew to ISS, because they also wanted to use this for ISS crew rotation. The service module, similar to Apollo, contained main power, propulsion, life support, etc. And that was storable systems, and that would perform the trans-Earth injection. It also had a spacecraft adapter and a launch abort system. Finally, the Altair lunar lander was sized to carry 4 crew members to the lunar surface. That was a 2-stage design. However, this is kind of the interesting part, that started to go with a hydrogen and oxygen stage. So that's why you can see there's some very big tanks here. And because that was a much more efficient system. And you also needed that efficiency because you're also performing that additional delta V with the lunar orbit insertion burn. The ascent stage, similarly, like that contained hypergolic propellants because that was going to be in space most of the time. And the idea behind this is you could land between 14 and 17 metric tons of cargo onto the lunar surface. So this was canceled in 2010. Now, this kind of survives in many ways, right? So Orion is now the multi-purpose crew vehicle. The service module that I just talked about, that's been replaced by a European service module with ATV heritage. And the second Orion to fly, we had the first test flight of Orion in 2014. So that was essentially the command module test flight there. And the second full Orion, that's currently being integrated at Kennedy Space Center on top of the SLS. So yeah, Ares 1 and 5 were canceled. The J2X was mothballed. I don't even know if that was tested. I forget, but that was never flown. And so the Ares kind of evolved into the Space Launch System. So we reused that 5-segment solid rocket booster. We're using RL-10s for upper stages. Based off that, the core stage should have said RS-68 for the core stage. I'm sorry. The original Ares had RS-68s. We replaced those with SSMEs because those didn't quite work out. We have an RL-10 derived upper stage. A larger upper stage is currently being designed, and that's would use 4 RL-10s. And so they announced this past week that they currently expect this to launch in February of 2022. So I have about 4 more charts. I just wanted to talk about what are we doing today. And so, as Robert Zumert said, right, the space industrial base has changed dramatically in the past few years. So SpaceX and Orbital ATK, now Northrop Grumman, have flown commercial resupply missions. SpaceX and Boeing were developing human-rated crew vehicles. SpaceX has since flown them and are now doing commercial crew rotations. First stage reusable rockets of Falcon 9 was demonstrated. We also have ULA's Vulcan Centaur, and Blue Origin was starting up liquid engine developments, and they're now flying people to space suborbitally. They've currently announcing the New Glenn. So whereas Constellation was really the idea of how could we leverage existing shuttle assets to go do lunar exploration, Artemis is very much how can we leverage the new space and commercial developments to do lunar exploration? And so that gave birth to the government reference architecture of the 3-element lunar lander. And so the idea there is that I have commercial launch vehicles that go to near rectilinear halo orbit. And so those will all aggregate there. And so this is interesting because you can actually do a very slow transfer. So you can spend 120 days in space at a much lower delta V cost, or I can spend a normal amount, quote unquote, normal amount of delta V to get there in 5 days. And so that makes the trade space interesting. So the idea here is, at least the going in idea, things are interesting in this world, still very political. But the general idea is that I could use something like a Falcon Heavy or a New Glenn launch vehicle to launch 3 smaller elements to NRHO that could then rendezvous with the Orion that was launched on the SLS to then execute a lunar mission there. So you can see the reference 3-element architecture here. So I would say they're currently in source selection for the Artemis program. So it's currently initially awarded to SpaceX solely. Blue Origin has protested the award. They lost that protest. They're now suing. The current Senate appropriation bill, and this is subject, they're currently negotiating this, so this could change by the minute. Last I checked in the news, they're currently directing that to fund 2 lander concepts, which people are saying might be Blue Origin. So Blue Origin is definitely using more of a 3-element system that I talked about before. So that's actually doing that similar reference architecture. They're partnered with traditional old space companies like Northrop Grumman and Lockheed Martin. And they are definitely using those launch vehicles, commercial launch vehicles for those elements. And they're using hydrogen and oxygen as a fuel in their descent elements. So you could definitely see the large hydrogen tanks in the picture from Blue Origin. I figure I would mention starships. That's a very different concept. That vehicle that has more in common with a launch vehicle than a lot of these in-space vehicles, right? So maximum that those other elements could be is around 15 to 16 tons, whereas Starship has 600 to 1,200 tons of propellant. And yes, I'm getting my engineering information from Elon Musk's Twitter, because that's how things are these days. So what's really amazing about this is that they're doing basically everything in single stage. So this is why I love this chart that. By the way, these are collaborators. I've known them for about a decade. They work at Marshall Space Flight Center. They do great work. So they're doing the full translunar injection to near rectilinear halo orbit, down to low lunar orbit, to the moon surface, back to low lunar orbit, back to near rectilinear halo orbit in a single stage. So that's over 9 kilometers of delta V. And in order to do that, there's an entire in-space cryogenic refueling system that they're working with the Starship system. So it's going to be very interesting to see how all this plays out in the next few years. And so this is kind of my final chart. So the next steps is that, hey, this survived a presidential administration change because there's bipartisan support for this. We should have clarity on contract awards in the coming months, and then it's on to the SLS Orion test flights and the development of the human landing system, where there's a lot of technology changes in there for that. So I think I've gone a bit long, so I'll say thank you, and I'll definitely be open to answering some questions. Thank you very much for your attention.
Hello.
Hello.
Hello. Yeah, thank you very much, Bradford, for your didactic presentation. It's been an excellent and complete explanation of the different designs of space vehicles we have at present. Really, in your presentation, all these complex systems seem to be very simple. We have a question from Rodrigo Suarez. The question is, are the new propulsion technologies going to be ready to work during this century? Which are the most developed so far?
So in terms of propulsion, right? So I mostly talked about chemical propulsion. in terms of, so it's more, this is going to become a lot more interesting in terms of going to Mars. So the general things that we're working on right now are going to be much higher thrust electric propulsion. So solar electric or nuclear electric propulsion and nuclear thermal propulsion. The three of those are all definitely going to be done this century. Right now, we're currently trading those types of propulsion architectures for Mars missions today. The United States government has made it a priority that they want to have a nuclear thermal propulsion demonstrator flown sometime in the next 10 to 15 years to actually demonstrate nuclear thermal technology. So just to give you all an idea, right? So a nuclear thermal rocket that utilizes hydrogen as its reaction mass. So I can't really say propellant, that's more reaction mass. That has an ISP of around 900 seconds, whereas the RL-10, the most efficient chemical propulsion system that we have, has an ISP of around, at its best, is around 460 seconds. So that is double the efficiency, and that's one of the things that would enable a Mars system.
Okay, thank you again. Yeah, we don't have any questions at this moment, but the chat is always open. So thanks again for your interesting and excellent presentation. The Chilean National Engineering Association appreciates your presence in this aerospace seminar and hopes to see you again in the future. And I invite you, of course, to see the next presentation and be attentive if we have some new questions. Thank you very much again.
All right. Thank you very much for your time, and thank you for the invitation. I wish all of you a good evening.
Okay, thank you.